In this section, we'll introduce Lagrange's theorem, which is an incredible restriction on the size of a subgroup of a group. And in order to do so, we'll need to talk about cosets. So let G be a group, and let H be a subgroup of G. Now, the main point of this lecture is that we'll see that the left cosets of H, which I'm going to define in a second, will partition G. So here's this G visualized as a big rectangle, and then we've got the subgroup H, and then if you look at these what's called left cosets of H, they'll cover up G evenly. They'll partition it. And okay, so here's the definition of a left coset of H. It's a set of the form G times H, where this lowercase g is an element of the group. And so simply, to form a coset G times H, you just multiply each element of H on the left by this fixed or specific element lowercase g. When we multiply on the left, it's called a left coset. When we multiply by G on the right, it's called a right coset. They're different in general, but for now we'll just stick to left cosets. Let's do a simple example. Let our group G be Z mod 7, the multiplicative group. In other words, its elements are the numbers 1, 2, 3, 4 up to 6, and the group operation is multiplication mod 7. So for example, 5 times 6, that's 30, and then you take the remainder mod 7, and 30 is 2 more than 28, so 5 times 6 is 2 in this group. Okay, now, and let's let H be the subgroup generated by 2. In other words, we take all the powers of 2, so 2 squared is 4, 2 cubed is 8, but we're in mod 7 land, so 8 is the same as 1, and so that's how I got 1 here, and then if you multiply 1 again by 2, you're back here. And this is the set 2, 4, 1, and when you write sets, the order that you list the elements in does not matter. So I could also write the set as 1, 2, 4. Okay, so here's our subgroup H. Now, what we have to do to find the left cosets of H is take these elements of the group and pick each of them and multiply the elements of H by them. So if I take 1 and to multiply each of these elements 2, 4, 1 by 1, obviously I just get the same thing, 2, 4, 1, so I just get H. Okay, let's take the element 2 and look at this left coset 2H. So all I do is take 2 times 2, 2 times 4, 2 times 1, 2 times 4 is 8, and in mod 7 land again, 8 is equal to 1, so we've got this. And so we've got the numbers 4, 1, and 2, and the order I list them in doesn't matter, and we see that we get the same set H. H consists of the numbers 2, 4, 1, and those are the same numbers here, just listed in a different order. So this left coset 2H is the same as the subgroup H. Okay, now let's look at 3H. 3 times 2, 3 times 4, 3 times 1, 3 times 4 is 12. 12 is the same as 5 mod 7, and so we get this. So this is a new coset we haven't seen before. So far we've just seen H and H. So 3H is a different coset. Then 4H, I didn't do the calculation, but I just suppressed it and did it elsewhere. And we get H back. 5H, if you work it out, you get 3, 6, 5, and that's the same, just listed differently, but for our purposes, the same set as 6, 5, 3. And if you do 6H, similarly, you'd get actually the same coset as 5H and 3H. And so what we've seen here is that our group, which consists of 6 elements, it's subdivided into the subgroup H and another coset. And the subgroup H is the left cosets H, 2H, and 4H. And then this other set here, 3, 5, 7, those form these left cosets 3H, 5H, and 6H. So left cosets we see in general might not be a subgroup. For example, this left coset here is not a subgroup because it does not contain the identity element, so it can't possibly be a subgroup. But more importantly, what we see is that the cosets of H, if they're distinct, they don't intersect and they partition the group G. Let's do another example. Now let's take G to be an infinite group, so the group of integers, and the group operation is addition. And we've seen that any subgroup of the group of integers is given by the multiples of some integer n. And to be concrete, let's take n equal to 4. So we've got this subgroup H, which is 4z, which is just the multiples of 4. So the elements in H are 0, 4, 8, 12, and then their negatives. Okay, and then but the left cosets of H are, okay, g times H, but the times is plus. That's our binary operation. So in this problem, we have to add elements of the group G to elements of H. Okay, so let's start with 0 as the value of G. 0 plus every element of H, we just get back H. Then let's take G equals to 1, adding 1 to all these elements of H. 1 plus -4 is -3, 1 plus 0 is 1, so that's how I'm getting all these numbers here. Similarly, 2 plus all these elements of H, you get these numbers. 3 plus H and 4 plus H are likewise. And the thing to notice is that, what's special about these numbers, for example, in the coset 1 plus H, they're all numbers that have a remainder of 1 when divided by 4. In other words, they're 1 mod 4, all the numbers that are 1 mod 4. Similarly, the numbers here, these are the numbers that are 2 mod 4. In other words, 2 more than a multiple of 4. Like you could say like 14, that's 2 more than 12. And so on. And if I didn't write out 5 plus H, but 5 plus H will be actually this same set here as 1 plus H, so same coset. And here's a picture, a schematic picture of our group Z, and how the cosets, they subdivide the group or partition with no overlap, unless the cosets are equal. So for example, the coset H, which is 0 plus H, that's the same as the coset 4 plus H. But H and 1 plus H, they have no numbers in common. So they're disjoint since they don't have any elements in common. Okay, so we've got the subgroup H and its 4 cosets, and they cover all of Z, the integers. So this is the main point of this lecture, is that the left cosets of a subgroup H partition the group G. And by partition, it means divide up completely with no overlaps, unless of course the 2 cosets are equal. Okay, so to show something partitions group G, so again, this is an arbitrary group, not either of the 2 examples we've seen, but okay, we have to show that every element of G is in some coset, and then also that distinct cosets don't intersect at all. Okay, so the proof of 1 is quite easy. If we have an arbitrary element lowercase g in G, then this element G is going to be in this particular coset, namely the coset G times H, because G times E, which is just G, is in G times H, and E is in H, because it's the identity element, and H is a subgroup. Okay, so then let's move on to the proof of the second point, which is a little more complicated, that distinct cosets don't intersect. Okay, so suppose we had 2 cosets, AH and BH, and they did intersect. And what we want to show is that the 2 cosets then have to be equal. In other words, every element of AH has to be in BH and vice versa. So suppose, again, the cosets did intersect, and let's say X is that common element they had in common. X is then in AH and X is in BH. So that means X is A times H1, and X is also B times H2 for some H1 and H2 in H that we don't really know more than that. And what we want to show is that AH is a subset of BH, and also that BH is a subset of AH. These 2 combined will then show that this set AH equals the set BH. 2 sets again are equal if they have the same elements, and the typical way to show that is to show that each set is a subset of the other. Okay, so let's focus now on showing that AH, this coset, is a subset of B times H. Okay, so in other words, we have to show that an arbitrary element of this left coset A times H is an element of B times H. Now an arbitrary element of A times H looks like A times H3 for some H3 in H. And what we want to show is that this arbitrary element A times H3 is equal to B times something. This is not something we know just yet, but, I should say B times something in H. Okay, so what we do know is that A times H1 is equal to X, and that's equal to B times H2. That's coming back from up here of our assumption that these two cosets intersected. And so we're trying to show something involving H. So let's take this equation, the A times H1 equals B times H2, and solve for A by multiplying on the left by H1 inverse. So I get that A is equal to B H2 H1 inverse. All right, and now let me go back here and look at A times H3. So A times H3 is equal to, I substitute in the value of A I found. It's this mess. And then the point is I have a B out in front, and then a bunch of elements of H that are being multiplied. And because H is a subgroup, all of these elements are in H. H1 is in H, so H1 inverse is in H. That's part of being a subgroup. And then when you multiply a bunch of elements in H, they stay inside H. That's again part of being a subgroup. And okay, so we've now shown that AH3 is B times something in H, and that's exactly what we wanted to show in order to establish this inclusion, that every element of A times H is an element of B times H. And now the other inclusion out here, B times H is a subset of A times H, is similar, and so I've omitted the proof. And that finishes the proof. So it immediately follows from the theorem we just proved, this corollary called Lagrange's theorem. Again, a corollary is something that immediately follows from a previous result. And Lagrange's theorem says, let G be a finite group. A finite group just means a group with a finite number of elements. And let H be a subgroup of G. Then the size of H, the number of elements in H, sometimes that's called the order, divides the order of G. And here's the proof, which is quite simple. The left cosets of H partition G into subsets of equal size. Here's a schematic picture down here. And because these all have equal size, we just immediately see that the size of H has to divide the size of G. In this picture, the size of H times 4 would equal the size of G. Just to give some more details, the left cosets of H have equal size. Why is that? Well, here's this claim that the size of the left coset AH is equal to the size of H, and that's because multiplication by A map that sends H to A times H is a bijection. It's injective because if I have two elements H1 and H2 in H, and they map to the same element in A times H, that means A times H1 equals A times H2, then I can cancel the A's, and that forces H1 to equal H2. And then this map is surjective, this map out here, is surjective by the definition of AH. It's just the elements of H multiplied on the left by A, so this map is surjective. And that's the proof. And then let me end with a simple definition of the result we just saw. Let G be a group, and let H be a subgroup of G. Define the index of H and G, denoted by this notation here, to be the number of distinct left cosets of H. So in other words, in this picture out here, the index of H in G is 4, because there's 4 left cosets. And the simple fact then is that the size of H times the index is equal to the size or order of G. And just rewriting that, we get this equation here, and again, this holds if H and G are finite groups.